In the vast, dark theater of our universe, the James Webb Space Telescope has just pulled back the curtain on a world that shouldn't exist, or at least shouldn't look the way it does. This discovery involves TY561b, a planet so extreme and broiling that it challenges our fundamental understanding of how rocky worlds evolve. TY561b is what astronomers call a super-Earth, a planet with a radius roughly 1.4 times that of our own planet. However, any resemblance to Earth ends there. This world is a member of a rare and brutal class of celestial objects known as ultra-short period exoplanets. To understand just how extreme this world is, consider its year. While Earth takes 365 days to orbit the Sun, TY561b completes a full journey around its star in less than 11 hours. This is only possible because the planet is tucked incredibly close to its host star, less than 1 million miles away, which is about 1/40th of the distance between Mercury and our Sun. At this proximity, the gravitational forces are so intense that the planet is likely tidally locked, meaning one side of the planet is permanently turned toward the searing heat of its star, while the other side faces the cold of deep space. On such a world, the day side is so hot that it far exceeds the melting point of rock, creating a global magma ocean. Before the James Webb Space Telescope turned its powerful gaze toward TY561b, scientists were already scratching their heads over its physical characteristics. The planet has an anomalously low density. In simpler terms, for a planet of its size, it isn't as heavy as it should be if it were made of the same materials as Earth. Initially, researchers like lead author Johanna Teskey considered that the planet might simply have an exotic composition, perhaps a smaller iron core and a mantle made of rock that is less dense than what we find on Earth. This theory had merit because TY561b is an ancient relic. It orbits a star that is twice as old as our Sun and resides in a region of the Milky Way known as the thick disk. This star is iron-poor, suggesting the planet formed in a very different chemical environment during the universe's youth. However, even a weird internal composition couldn't explain all the data. The team began to suspect that the low density was actually an optical illusion of sorts, that a thick, puffy atmosphere was surrounding the planet, making it look larger and less dense than its solid core would suggest. To solve this mystery, the research team used Webb's near-infrared spectrograph to perform a temperature check on the planet's day side. They used a technique where they measured the decrease in the brightness of the star-planet system as the planet moved behind its star. The logic was simple. If TY561b was just a bare, airless rock, the day side should be cooking at a staggering 4,900 degrees Fahrenheit. If the planet had an atmosphere, that air would act like a thermal blanket or a circulation system, moving heat around the planet and lowering the peak temperature. When the data came back, the results were definitive. The day side was approximately 3,200 degrees Fahrenheit. While still hot enough to melt most substances, it was far cooler than a bare rock should be. This was the strongest evidence yet for a thick atmosphere on a rocky planet outside our solar system. Finding an atmosphere on a planet that orbits so close to its star is revolutionary. Normally, the intense radiation and stellar winds from a star would blast a planet's atmosphere away into space over billions of years. So, how does TY561b keep its blanket? The researchers, including co-author Angeli Piet, believe the planet must have a thick, volatile-rich atmosphere. This atmosphere likely contains water vapor that absorbs near-infrared light, and it might even feature bright silicate clouds that reflect starlight back into space, helping to cool the planet. Furthermore, the planet appears to be in a state of dynamic equilibrium. Co-author Tim Lichtenberg describes the planet as a wet lava ball. In this bizarre environment, gases are constantly escaping the atmosphere into space, but they are being replaced by the magma ocean below. As the molten surface burps out new gases, it simultaneously sucks others back into the interior, creating a cycle that maintains the atmosphere despite the star's best efforts to destroy it. The significance of TY561b goes beyond just one hot super-Earth. This research is part of Webb's General Observers Program 3860, which involved watching the planet continuously for over 37 hours, enough time to see it complete nearly 4 full orbits. This discovery challenges the prevailing wisdom that small rocky planets located so close to their stars are destined to be bare rocks. It suggests that the chemical environment of the early universe, where this planet formed, might have allowed for the creation of planets that are much more volatile-rich than Earth. By studying TOI 561b, scientists aren't just looking at a weird exoplanet. They are looking at a time capsule from an era when our galaxy was young. It provides a window into how planets form and retain their atmospheres under the most hostile conditions imaginable. The team is far from finished. They are currently analyzing the full 37-hour data set to create a map of the temperature all the way around the planet. This will help them narrow down exactly what the atmosphere is made of, whether it's dominated by water vapor, rock vapor, or something even more exotic. As researcher Johanna Teskey noted, the most exciting part of this data is that it is opening up even more questions than it's answering. To understand the relationship between TOI 561b's magma and its sky, think of the planet like a pot of thick stew simmering on a high-heat stove with the lid slightly ajar. Even though the heat is intense enough to dry everything out, the liquid, the magma ocean, is constantly releasing steam. That steam keeps the top of the stew from getting scorched to a crisp, while some of the moisture drips back down into the pot to be heated all over again. It's a violent, bubbling balance that keeps the pot from ever running dry. The discovery of TOI 561b represents a major shift in how we understand the survival of planetary atmospheres. While scientists previously believed that small planets orbiting so close to their stars would inevitably be stripped of their air, the thick, volatile-rich atmosphere found by the Webb telescope proves that these broiling worlds are far more resilient than we imagined. Ultimately, this wet lava ball is more than just a celestial curiosity. It is a window into the ancient history of the Milky Way. Because it orbits a star twice as old as our Sun, TOI 561b provides a rare look at how planets formed in the iron-poor chemical environments of the early universe. By showing us that a world with a global magma ocean can maintain a substantial blanket of gas, the James Webb Space Telescope is challenging prevailing wisdom and forcing us to rewrite the rules of planetary evolution across the galaxy. If you want to stay updated as the James Webb Space Telescope continues to solve mysteries in our solar system and probe the mysterious structures of the distant universe, make sure to subscribe and hit the notification bell. We are in a new era of discovery, from exploring impossible atmospheres on rocky worlds to following NASA's journey from the Moon to Mars and beyond. Join us as we continue to uncover the secrets of our place in the cosmos.